In our last video, we used position and velocity versus time graphs to develop several useful kinematics formulas. That were these. These four formulas, in specific, are probably the most useful for problem solving when we're talking about motion. In today's lesson, we're going to show you how you can use each of these four equations to answer a problem. The situation is this. Suppose we have a plane on a runway. It's sitting there at rest, and then it starts to accelerate at 2.5 meters per second every second. It must reach 80 meters per second before taking off. The questions are simple. How much time is required before it can take off? And also, how much distance or how long must the runway be? For most kinematics problems, the first thing I'll do is set up a table of things that we know and also things that we might have to make assumptions about before proceeding. The table always involves 6 different quantities. They are the initial position, F0, the final position, SF, the initial velocity, V0, the final velocity, VF, the acceleration that the object is experiencing, and the amount of time. Now, when we look back at the problem, there were 2 numbers given to us. The first number was this 2.5 meters per second squared. The meters per second squared and the word acceleration there is clues that this is an A, and so we'll put that in as 2.5 meters per second squared. The other number is 80 meters per second. 80 meters per second is definitely a velocity. Is it the initial or final velocity? Well, this is the speed it requires. It's required to reach before taking off, so that would be our final velocity. And the rest of these numbers we either have to make some assumptions about or calculate. The time required is definitely something we're going to have to find. That was one of the questions that was asked, so I usually put a blank there. The initial velocity is actually told to us. You don't specifically see a number anywhere, but this phrase, at rest, leads us to believe that the initial velocity is 0. And this particular problem is a very typical problem in the fact that we aren't told anything about the initial position. When that's the case, we usually set the initial position to be 0. Therefore, the final position will be the total distance that the plane traveled. That final position, SF, is something we'd have to look for, so again, I'll put a blank there. Once I've completed this table of knowns and assumed and unknowns, now I'll start to look and see if there's any equations that we can use that might help us. Here's those formulas that we had derived. And the first thing I notice is that we know everything in this first equation except for time. We were told the final velocity, we assumed the initial velocity, and the acceleration was told to us as well. So I would suggest we use that equation so we can calculate time. Typically, anytime I use a formula, I will first write the formula down. This is very helpful to your teacher to know what you're thinking and what you're trying to accomplish. Then, underneath it, I will start to put in the numbers from the problem. So, in this case, 80 is our final velocity. 0 was our initial velocity. And the acceleration is 2.5 times t. And at this point, we start to use algebra to solve for the variable. This 0 didn't really have to be written, and this is a pretty simple equation. Divide both sides by 2.5, and we get a time, and that time is simply 32 seconds. Now, to find the final position, we've got a couple different equations at our disposal. The next 2 equations are set up to solve for final position already. You see SF equals on the left-hand side. This first one I typically call the SO vote for AT&T formula because it's got SO and VOT and it's got ATT in there. Don't forget the half, of course. But that's probably the most common equation that we use in kinematics problems like these. This second equation is possible if you know what the average speed is along the way. We weren't told the average speed, but since it's accelerating constantly from 0 to 80, we can find the average easy enough. That's just 0 plus 80 divided by 2, which is 40. And even though this final equation is not specifically solved for SF, it has SF in there, as well as every other thing, as well as final velocity, initial velocity, acceleration, and starting position, which we all know already. So we could use that as well. I'm going to show you how to use all three equations, although in general, for this particular problem, I would probably just use this second equation and be done and move on. To find the final position then, let's begin by writing the formula. Final position is initial position plus v naught t plus 1/2 at squared. And then we fill in some details. SF is our variable, but f naught is 0, which means this particular term can be neglected. 0 plus anything, it's just going to be anything. The initial velocity is also 0, so 0 times 32 is just 0, so this term doesn't really need to be in this equation either. And so we're left with 1/2 times the acceleration, which was 2.5, times 32 squared. And we can calculate that answer quickly. 1/2 times 2.5 times 32 squared. And that's 1,280. And the units of that answer, since it's a final position, must be in meters, because meters is the standard unit for position, and every other number that I plugged in here was also in standard units. Now, let's verify that distance by using one of the other equations. How about the average velocity equation? That's SF equals average velocity times time. The average velocity when there's constant acceleration is simply the starting velocity and the final velocity added together and divided by 2. So 0 plus 80 over 2, that's 40 meters per second is our average velocity. And our time is 32 seconds. If we multiply 40 and 32, we also get 1,280 meters. Typically at this point I would definitely move on, but because I want to make sure you've also seen how to use the no time formula once, I'd like to calculate one more time our final position and see if we can verify it with that third equation as well. So once more, I'll write the original equation. That's VF squared equals V naught squared plus 2 times A, and SF minus S naught is the distance that's required. You can write SF minus S naught if you'd like, but in this particular case it'll be faster to just write a D, the distance that we've traveled. And now let's plug in some numbers. The final velocity is 80, and that's squared. The initial velocity is 0, and 0 squared is just 0, and 0 plus something is just that, so this term can be ignored. And we're left with 2 times the acceleration, which is 2.5, times the distance that we traveled. 80 squared is just 8 times 8, it's just 6,400, which is equal to, and here 2 times 2.5, that's 5D. And divide both sides by 5. 6,400 over 5, and look one more time, we get the same distance of 1,280 meters.